Hey, AP Chem, we are wrapping up Unit 7 with our kinetic stuff by circling back around to reaction mechanisms. Now, I told you at the very beginning we would come back to these again after we talked about all the stuff, and here we are. So what we're going to actually do today is we are going to tie together mechanisms and the rate law, because we've been kind of dancing around it a little bit, but a mechanism actually will, if it's done right, match up with the rate law that's determined experimentally for a reaction. And that is actually the key to saying a mechanism is legit. So the rate law that we determine experimentally, either through integrated rate law techniques or method of initial rates, has to tie into our proposed mechanism. And this is kind of how it works. So when we talk about a mechanism, we know that the individual steps of the mechanism are called the elementary steps. And so when we are trying to take a look at the rate law and then tie it together with the mechanism, what we always have to do is we have to take a look at the slow step. We've talked about this before, how the slow step is going to be our rate determining step. And when we talk about a mechanism, the elementary step, that's the slow step, is where we are going to find our rate law. So the actual reactants in that slow rate determining step are what we are going to use to write our rate law. And so what has to happen is the coefficients, and again, this is the only time this happens, the coefficients in our rate law actually become our orders in our rate law. So I think I said that backwards. So our coefficients in our balanced equation for the elementary slow step matches up with the order in the rate law. Now you're going to sit there and you're like, give me some context here. So we're just going to kind of dive right into an example, and then I will show you what I mean. So pardon the blurry graphic here, but this is a proposed mechanism for the overall reaction for HBr turns into, or plus O2 turns into 2H2O and 2Br2. Now we are technically missing a step here. So this 2 here happens twice in this mechanism. But when we take a look at all of the steps, kind of like we've talked about before, we cancel out things that are duplicates, and then we add things up that are the same on both sides. Cancel out on opposite sides, add things on the same side, and it gives us our overall reaction. So in this particular mechanism, it suggests that our slow step is HBr plus O2 turns into this guy here, HOOBr. And then that HOOBr reacts with another hydrobromic acid, HBr here, to turn into 2 HOBrs, and then those two react with more hydrobromic acid to turn into water and Br2. So that's our mechanism for this whole process. When I want to write a rate law and I am looking at the mechanism, again, I only pay attention to my slow step, and that's it. I don't pay attention to the overall reaction. I don't pay attention to the fast step at this point. We're only going to be paying attention to the slow step. So what ends up happening is that our rate law is just these 2 reactants included in the law with orders that match their coefficients. So you can see a 1 and a 1 here, or you can't, but they're implied. And so what happens is our rate law becomes rate equals K, our constant, times the concentration of HBr times the concentration of O2. Again, I cannot emphasize this enough. This only works for the slow elementary step of your reaction mechanism. Your overall reaction does not work like this. As you can see, HBRs and O2s, like there's a 4 here, there's definitely not a 4 here. So it only depends on how the things in your slow step react together. And because of the coefficient, that coefficient literally represents the exact collision that's happening. If we'd have twice as much, it would affect it by a factor of 4 for our rate. So in this case, again, our rate is rate equals K times the concentration of HBr times the concentration of O2, and both of those are to the first order. Overall, our reaction is second order. We could figure out our rate constant if we had some data, and we could move on from there. Just as a refresher, our intermediates in this case are going to be HOOBr as well as HOBr because they are produced as a product and then used up immediately in the next process. And so both of those are our intermediates in this case. Okay, so it's a very specific thing that they're asking you, but this is how we prove that a mechanism is possible. So if I do the experimental work and I look at this and I get this from actually running the experiment and collecting some data, and then I propose this mechanism and the slow steps coefficients match with the orders here, that means that this is a plausible mechanism. So that's kind of the rules for a mechanism. Does the data support it from the experiment? And does the mechanism support the rate law that you get from the experiment? Yes, then in theory, it's plausible. Again, things that make a mechanism not so plausible would be like if I had 5 molecules that had to collide exactly at the same time in an elementary step. That's probably not going to work so well. But since I have 2 things that are hitting in this step, they match my data and they're the slow step, it makes this a pretty good mechanism. Now, when we start talking about these, the slow step most of the time is written first. And sometimes you get a fast step and then a slow step. And we're going to address that in class specifically because it's kind of its own mess that I don't really want to get into on a video. So we will talk about that in class specifically. Are they going to ask you a question about a slow second or third step? Potentially. And like I said, we'll dig into that a little bit later. So here is the example that I'm going to work through with you guys. There's kind of 2 parts. So this is, as you can see, it starts with C and then gets into D. And then we'll get into E and F as well. So this is part of a reaction, part of a problem that's, several parts that we're missing here because they're thermodynamic things. So the one thing that I need to let you guys know is that overall this process is going to be an exothermic step or an exothermic process, and that's going to be important for our graph that's coming up. So if you look at this first part here, it says it's proposed about the formation of this 2-step mechanism, and it gives you 2 steps. It tells you the first step is our slow step, then it asks us to write the rate law and identify an intermediate. And then we are going to draw a curve that shows the energy changes during the reaction. And then we're going to indicate the activation energy. So you guys can probably predict. I'm going to get my camera up here and then we'll dig into this. Okay, so this first part is what we just talked about here. It says to identify, it gives us our steps here. And then it tells us to write a rate law for the reaction that is consistent with the mechanism above. So again, we always find our slow step, our rate determining step here. And then our rate law is going to include any reactants that are in here, and then it's going to match its coefficients for each of the reactants with the order. So I am probably not going to have a lot of room. I'll squish it in down below here. So my rate law is going to be rate equals K. Now remember, this is just kind of the generic rate law. So it's just the generic part. So it's rate equals K. And then it's one reactant, C2H4, times my other reactant, and then HCl. And then when I take a look at these in here, I see coefficients of nothing in front, which means that they're 1s. And so our order for each of these is going to be a 1 as well. It's literally as easy as that. But you have to remember, this only works for the coefficients becoming the powers here in an elementary step from a mechanism. If it's not that, it doesn't work. So you cannot take just a regular balanced overall equation and pop those numbers in there. That's illegal. All right. So then for D, it says identify an intermediate in the mechanism above. So we are looking, I'll give you a second to look at it. Okay, so we go from here, we make these 2 products, and then they immediately react and turn into our actual product. So either of our intermediates in this case could be C2H5 or Cl-, and they said to identify an intermediate, so there would be either of those. The one thing that I can tell you is that they would be pretty fussy about the charges. So you have to include that charge. Otherwise, you probably aren't getting your point there. All right. So I had said before that this was an exothermic reaction. So it says using the axes provided, draw a curve that shows the energy changes that occur during the progress of the reaction. The curve should illustrate the proposed two-step mechanism and the enthalpy change of our reaction. So we know exothermic starts high, ends low. We want to drop in energy overall. And so we know that it's a two-step mechanism. So when we think about our changes, the slow step always has the big activation energy. Glad I left a lot of room. And then the second step is smaller there. So I've got a big step and a little step. This is each step of the mechanism. So we've got to have two steps. We've got to end low, start high. And then the big thing is that our slow step needs to have the biggest activation energy. And for F here, it says indicate the activation energy for the rate determining step. So activation energy is always going to be from where we start to the top of our peak. That's our activation energy, which we can write as EA. All right, so that's kind of a quick little FRQ having to do with reaction mechanisms. Like I said, we will discuss a fast first step and a slow second step in class. So take a look at this stuff, give your homework a try, or, I guess come to class with any questions and we will get things cleared up. All right, good luck.